9-54. All right, so 9-54, repeat. Where am I? Okay, sorry, wrong one. 9-54 is a air standard diesel cycle, has a compression ratio of 18.2. Air is at 120 degrees Fahrenheit, 14.7 psia at the beginning of the compression process and at 3200 Rankine at the end of the heat addition process. Counting for the variation of specific heats with temperature, determine A, the cutoff ratio, B, the heat rejection per unit mass, and C, the thermal efficiency. Okay, so what do we got? We got the air standard diesel cycle. We got a compression ratio of 18.2. They say the temperature at the start of the compression process, the beginning, is 120. I'll label that 1 for now, and you'll see why. And then the start for the pressure is pressure 1, and I'll show why we label it 1 in a minute. 14.7 psi. Okay, and then we have the temperature at the end of the heat addition process. That's going to be temperature 3. Okay, and maybe you're unsure right now what state that is after the end of the heat addition process. So then you can just, All right, so then you can just leave it as a T temperature, and then maybe you call it end of heat addition, or you just circle it and say, when is this? And we'll figure that out in a minute. And then it says use variable specific heats, okay? All right, so variable specific heats, and they want us to find A is the cutoff ratio, which is our subscript C. B is the heat rejection. Per unit mass, so it's lowercase q. That's the best I can do. All right, and then C is the thermal efficiency. Okay. Under analysis. All right, so then the first thing we want to do is TS or PV in a TS diagram. Okay, we have a cycle. We know it's the diesel cycle, right? So we got to know what that diesel cycle is. Okay. So we'll have our PV diagram. Start out at pressure 1. And we isentropically compress it with terrible curved lines. All right, I think that's the best I can do. State 2. Okay, so we have low pressure, low temperature at state 1, the highest volume. We've ended the intake stroke, and we're right there, state 1. Now we isentropically compress it, so our entropy is constant during that process. Okay, now we get to 2, and we have our constant pressure heat addition. Okay, pressures maintain constant from 2 to 3, right? We have our heat in, right? The Otto cycle is simpler. It's a constant volume heat addition, so 2 to 3 goes up, okay? And the analysis ends up being simpler too because of that. All right, 3, now we go to 4, we isentropically expand. Okay, and again, this is S is constant here. All right, and then 4 to 1, we reject heat in that exhaust blowdown process. Okay, so we have that. Where do we think there's a heat in? Or sorry, we have a heat in. Sorry, where do we think there's a work in? So diesel cycle is a closed system, and all our work is from boundary work, right? From the boundary moving. So where do we have a work in that we're doing?
One to two.
Yeah, 1 to 2. Is a work in, right? Where do we have work out?
3 to 4.
3 to 4. Yep, we're expanding there. Anything else? Any other place? So anytime the volume changes, we have boundary work. Okay. So we also have it from 2 to 3. Okay, so we have work and heat in 2 to 3. Okay, where in a Otto cycle, it's constant volume heat addition, so your 2's, it goes up to 3. So there's no work occurring while you're adding heat. But in the diesel cycle, it is because it's a constant pressure process. All right, so there we have kind of our laydown or our lowdown, and we can look at now we know that state 3 is the end of the heat addition process, right? So that's why we labeled it 3 in the givens, or maybe you didn't know that. Now you put your label in that it's subscript 3. All right, next we'll do the TS diagram. We got 1, and we isentropically compress in the closed system to 2. So S is kept constant, raise the pressure and temperature. Now we have a heat addition at constant pressure. So we go left to right because we're adding heat, we're adding entropy to the system. And then we have isentropic expansion from 3 to 4, so we're keeping S constant. And then 4 to 1 is our heat rejection. Okay. So we have Q in, Q out. So the PV diagram, you can see it's very easy to see where the work is. Anytime you're moving away from the same volume, you have some boundary work, right? You have a change in volume, you have boundary work, right? And the TS diagram, it's very easy to see where the heat transfer is. right? Anytime you have a change in entropy, you have a heat transfer, right? You add heat, you're going left to right. You reject heat, you're going right to left because you're decreasing entropy when you reject heat, increasing entropy when you're adding heat. All right, so now we have a really good idea of what this diesel cycle is, so we can analyze it, okay? So part A is the cutoff ratio, right? We'll start off, there's the compression ratio, right? That's just R. R is max volume over min, which in this case, max volume is 1 and 4 are the same volume, and min is 2, right? We could do specific volumes since the mass is the same, it's a closed system. We could do 4 here because it's 1 and 4 are the same. So that's compression ratio, right? Now we need what's the cutoff ratio. What is that defined as? Does anyone remember? The compression ratio told us about relating the smallest volume to the max volume. Well, we have state 3, that's right here, right? So it's not at the smallest volume or the largest, somewhere in between. And that's what the cutoff ratio defines, is volume 3 divided by 2. So it's relating this 3 to 2 here. And again, we can use specific volumes, okay? All right, so now we have the definition for cutoff ratio, and this is what we need to solve. Where do we go next? Any ideas? What type of fluid do we have in this cycle?
An ideal gas.
So we have an ideal gas, right? So that means we have, because it's air standard cycle, so there's an ideal gas assumption to it. So we have the ideal gas law then, right? So we have PV equals RT with the specific volume version. V equals RT over P, right? So we can see what that gets us. We have R T3 over P3, and now we're dividing by specific volume at state 2. That's a little cumbersome, so let's make this look a little nicer. Okay. All right, so we look at that. Gas constant. Boom, gone, right? Anything else we can cancel?
The pressures should be the same.
Correct. So we have a diesel cycle. The pressure's identical from 2 to 3, right? In the Otto cycle, we wouldn't have that, right? The pressure's changed, okay? But from 2 to 3. Okay, so the pressure's the same. So we get then just that T3. Actually, let me write this below. T3 divided by T2 is the cutoff ratio, okay? and T2. Well, T3, right, was a given. Right, the temperature after the heat addition. Okay, so we have that. Right, we're looking for the cutoff ratio. We need T2. One of the things, if hopefully you're writing notes, and if you're not, just using mine. In these cycle problems, it's difficult because there's lots of steps to see what's going on. So you might want to at least write down the givens, finds, and then the diagrams or the PVTS or if I draw a diagram when we get to the open systems. So then it's easier to answer the questions because that's kind of where you got to look for a lot of these answers in your equation sheet versus when I'm here, you only see this small part of the board or of what I'm writing. Like if we're in class, in a classroom, I'd have try to use the whole board when we do these cycles so you can see different parts and look around at it. But we don't have that benefit right now. All right, so go ahead. Sorry.
I think I figured out how to find temperature too. Using the 18.2 value, set that equal to V1 over V2, and then just solve for the temperature too, because it's an ideal gas.
As an ideal, so ideal gas law. Okay, let's look at that. All right, so we have PV equals RT, right? So if we keep R's are constant, so we know then P1, V1 over T1 is P2, V2 over T2, okay? Well, we're given T1 and P1, right? We're looking for this T2 where we also don't know P2, right? We can, as you said, divide the volume. So we could do V2 divided by V1, like move the V1 over, and then you would have compression ratio, right? So if we rearrange this, so let's just do this. P1 over T1 equals P2 over T2, and then V2 over V1. That's compression ratio right there, right? But we don't know P2 or T2. So we still have two unknowns with this equation, okay? So the ideal gas law is really good if we know one of the pressure, if we know the pressure, temperature, and then obviously we know the other state temperature and pressure of the other state, so state one. But if we know one of the pressure and temperature, then we can get the other using the ideal gas law and relating it to another state. So if we knew temperature, now this is the easy way to get pressure. Or if we knew pressure, this is the easy way to get temperature. But since we don't know that yet, we got to use something else to get us there.
Would we use the conservation of energy to figure out like the boundary work?
We can to figure out work, but because work is also, if you use conservation energy, work is also an unknown in that equation, right?
Oh,
we
you're
wouldn't
right.
know work is an unknown, and then
We could have done the change in pressure. That's, oh man.
Yeah. So what do we do? So it is going from 1 to 2, but what else do we know about that process?
The entropy is constant.
Yeah. So we know. Yeah. Go ahead.
No, I was right. Entropy is constant.
Okay. Entropy is constant, which means it's a isentropic process. from 1 to 2. S is constant. So we have isentropic relationships. But it's variable specific heats. So we can't use any of them that have CP, CV, or the ratio of specific heats, K. So we have two equations for this. We have one that relates pressure, one relates temperature, okay? And then we have table A-17E. Okay, for the values that we need for relative specific volume or relative pressure. They're in the air tables. Okay. Basically, it's the same isentropic equation that has constant specific heats, but it didn't make that assumption of constant specific heats. It stopped and rearranged it to a form that looks like this. Okay, from chapter 7. Okay, so in this, we are a closed system, so we're looking at the diesel cycle, a closed system, and as we saw, we were able to use compression ratio in the ideal gas law above. So we want to use that version again. Okay, so open system, we would typically use the pressure one, closed system, the volume one. Okay, so let's rearrange this for something for state 2. And as we said, this is the compression ratio. So we have that. We need this and this. So if from table A-17E, we can, knowing temperature 1 is 120 degrees Fahrenheit, which is 580 Rankine, we can just go to that table and look up what that relative specific volume is, and that's 120.70. Okay, so that means we have this. So now we plug in our compression ratio, it's relative specific volume, we get the second one. We get the one at state 2. Which is 6.632. Which tells us the relative specific volume at state 2. And then that we can use the table and get T2. Because all these, at any temperature, everything, because it's an ideal gas, everything is only a function of temperature. Okay, so it's not a function of another property. So it doesn't need two independent intensive properties like water does or refrigerant. It's an ideal gas, so it only requires temperature to get all that other information. Everything's just a function of temperature. So we have this relative specific volume, which is a function of temperature. We solve for it. Now we can get T2. So we get 1725.8 Rankine. Okay. So then we come back, we have T2 and T3, so we can solve for our cutoff ratio. and we get 1.854. Okay. Now we have part B, which is the heat rejection. Q out, or heat rejection per unit mass, so lowercase q out. We go back again to our diagrams. How do we solve for that? Where do we start?
Process 4 to 1.
Yeah, so 4 to 1 is where we get heat out, right? So we solve for heat. We want to do a COE for process 4 to 1. Right? So we have process 4 to 1. The COE closed system. In the air standard cycle, we're neglecting, oh, I have 2 kinetic energies. So we hate kinetic energies, so we're neglecting it twice. We have kinetic and potential that we're neglecting, okay, in the air standard cycle. And then it's a closed system, so we can divide out mass, right? So we can make this lowercase if we want to. All right, in the second state, state 1. And that process in the first state is state 4. All right, so now we have this. Is there anything we can simplify, cancel?
The volume's constant, so there's no work.
Yeah, so there's no boundary work, right? Okay, so then we just have Q is equal to U1 minus U4, right? So we need U1 and U4. Well, how do you think we get U1, the internal energy at state 1?
We know temperature too, so maybe using that ideal gas law, where it's like changing U equals specific heat times changing temp.
No, because that would require constant specific heats. So the delta U equals CV delta T. That requires, so we can't use this because that's constant specific heats, right? So we have to get this value directly, okay? And that is from this table again. Okay, so we have temperature, we go to that table. You can read off U1 directly. Where is it on my sheet? So we get 98.20 BTUs per pound mass. If we were solving the cycle with constant specific heats, which we will solve some of these cycles that way, or I usually flip the ones we do in class of variable specific heats on your homework. You got to do them with constant specific heats. So then we could use that CV delta T. Okay. But this one said use variable specific heats. If it said use constant, we could use constant. If it didn't say variable or constant, then we get to assume what we want, right? We just make our assumption and we go with it, right? Variable specific heat's more accurate. Constant specific heat's is a little easier to get an answer. Right? All right, so we have U1. So now we got to get U4, which requires, just like state 1, we were able to get it because we had information at state 1. State 2, we have information, so we have a temperature, so we can get everything we want there if we needed to. But now we need to figure out stuff for 4. Okay, let's go up to there. Any ideas? We can't use a CUE because we're using that right now, right, to solve for Q out. And it has 2 unknowns. So we need something else, right? The way to look on these diagrams is you're usually either going, like we got information about 2 because we used stuff at 1 to get to 2, right? So you have to either use the state in the process after it or before it, right?
3 to 4.
Yeah, 3 to 4. All right, so 3 to 4, what do we know?
That entropy is constant.
Yeah, so we have that isentropic process from 3 to 4, okay? So we, again, use our variable, our isentropic relationships for variable specific heats. So if we have this one, it's VR4, VR3, V4, V3. All right, so we need to figure out everything here, right? Can we get the relative specific volume at state 3? How did we get it for the other ones? How about for state 1? How did we get it?
Using the cutoff ratio, can we get it like that?
Not for VR. This is just a relative specific volume, so this is just a table property. This is where this side is where we might have to use that cutoff ratio, but the relative one is this one, sorry.
Oh, for the relative, I didn't notice the R.
Yeah. What do we know for state 3?
Temperature.
Yeah, so we know temperature. So we know temperature, we know all the properties in table A17. Since we know T is equal to T3, it's 3200, then we can get VR3, okay? And that is 0.955. Yep. All right. So we have that. Now this is where what was said is the cutoff ratios, where we got to kind of use that, right? So the cutoff ratio is V3 over V2. Okay. So if we rearrange for V3, we have this, right? If we plug that in, let's make that a better. So we have relative specific volume at 3. We've already solved for the cutoff ratio. Any information for V4 over V2? Do we know what that is?
Is it the same as V1 over V2?
V1 over V2? So V4 over V2, right? We said. It's the same as V1 over V2, yeah. So, yep, because you are V4 is the same as 1, right? And then you have V2, right? So that is what? Right here, our cutoff ratio, or not, our compression ratio, R. Okay.
Is it just 1 over the compression ratio?
No, so we have V4 over V2. So it's just the compression ratio. Large volume divided by small volume, right? Because compression ratio is 18.2, so it's going to be large volume, which is 4 or 1, divided by small volume, which is 2, right? So then we have this. So that one required a little bit of manipulation. I'd say it's a trickier one to get that state 4. But to know that why you can is because we have a ratio defining 4 and 1 in volume to 2, and then we also have one that defines 3 to 2 with the cutoff ratio, right? So then we should be able to use those two to get a ratio from 3 to 4, and that's what we did, okay? All right, so now we have everything here. So we plug them in. We go beep, boop, beep, beep, boop, plugged it in, and we get 9.375. All right, so what good is that?
So now we can look up U4 in the table.
Yep, so we have that table. The table tells us all. So now U4 272.58. And we go back up. We have heat. So we get negative 173.7 BTUs per pound mass, or if we want to call it Q out with that subscript, then it's just 173.7 without the negative sign. Okay. Because the subscript out tells us the direction then. All right. What is next? We have thermal efficiency. So per unit mass, because that's what we're working on in this problem, but it could be capital W, capital heat transfer. All right. So if we look at this, we have work net over QN, right? We don't have either of those, right? So let's see if we can manipulate this a little bit. Work net is also related, right? If we go and make our boundary around the whole cycle like that, we have work out crossing, work in crossing, we have Q out and Q in crossing, right? Well, all work net is all the works together, which is equal to then Q in minus Q out, like we did in chapter 6. Okay. Or if we divide both terms by Q in, we get 1 minus Q out over Q in. All right. If we wanted to use work net directly, that would have been work 2 to 3 plus the work from 3 to 4 minus the work from 1 to 2. Okay. So if we do works, we have all these together. That gives us the net work, right? Work in and the work out. So that would require us to solve for Q in and then each of these works. So we'd have 4 unknowns in this equation, okay? So we used the COE on the whole cycle to get that those works would just be equal to Q in minus Q out. And then we just have Q out over Q in, and we already did the Q out because it asked us for it in part B. So now we need heat in. So what do we do for that? How do we get the heat in, or where do we start?
COE of a closed system,
Yeah, for which process?
or 2 to 3.
Yep, so we have process 2 to 3, our heat addition process. We have COE closed system. I'm going to start with the per unit mass version with kinetic and potential already canceled. So we have this, right? Can I cancel the work?
No.
No, we have boundary work occurring, right? What type of boundary work do we have?
Work out.
Yes, so it's a workout, right? So we're getting expansion work during that. But is anything being held constant?
Pressure.
Yeah, pressure, okay. Let's say constant pressure heat addition. So that gets pulled out of the integral and we get P delta V, okay. All right, so we have delta U plus P delta V. That's the same as enthalpy, right? Since pressure is held constant, again, for that process, it ends up being the same as enthalpy. All right, so then we just have enthalpy at 3 minus the enthalpy at 2. Can we get these? Or how do we get these?
Yeah, we can get them from table 17.
Yeah, so we've described and figured out something for each of the states, right? 1, we have temperature and pressure was given in the problem. 2, we figured out the temperature, well, relative specific volume, which then gives us temperature. So then we could use that to get our enthalpy. And then state 3, we figured out the we were given temperature, so we could use that to get our relative specific volume earlier, but we can also then use that to get our enthalpy at state 3. We get 849.48. All right. So we have H3 and H2. So we get then for our heat in, .9 BTUs per pound mass. So we go up, we have heat out, we have heat in, so we can solve for our thermal efficiency. So we get 0.586. Or 58.6%. Okay. Any questions? So if we had constant specific heats, we would put Cp delta T for enthalpies, right? Or Cv delta T for internal energy here. Or when we were looking for, so right here, isentropic relationships, we have the constant specific heat versions on your equation sheet, which has the ratio of temperatures and then ratios of pressures with K divided by K minus 1 or K minus 1 divided by K, I can't really remember. So it has those versions, which are the constant specific heats for a isentropic process. So we have that path to get our properties, okay, with constant specific heats. The other difference is if we had the Otto cycle, looks like this, where you have and it's simpler to analyze because the heat addition process from 2 to 3 is at constant volume. All right, and everything's occurring just at the largest volume or the highest volume. So compression ratio is the only thing you have to worry about. And then the heat in, there's no boundary work, so it ends up being delta U, change in internal energy, just like the heat out, because it's both at constant volume. Okay, it's the diesel cycle that has that extra complexity because of the constant pressure heat addition process. Puts 3, over at a different volume, and we have work and heat occurring during the heat addition process, where here we just have heat, okay? But it's still S is constant. So 3 to 4, 1 to 2, entropy is still constant for both of those. Same thing, isentropic relationships, okay?
What cycle was that again?
This is the Otto cycle. So it's this kind of the spark ignited engine cycle. So the same analysis with the Otto cycle would have probably taken about half the amount of work. right? Because a lot of it was because we had cutoff ratio, which you don't even have to worry about. It's just compression ratio because it's all the largest to smallest. And so cutoff, you wouldn't even have to worry about rearranging. This would already work because it's already at the compression ratio. When you get to, when you need information for state 4, okay? All right, so that's it. Oh, sorry, go ahead.
Sorry if you said it earlier, but do you want us to have those like cycles memorized? Because I know it goes like heat in, heat out, work in, work out, and it's like I don't remember, like maybe 5 cycles. Do you want us to have those memorized, or do they vary, or are they always exactly the same?
Well, if it's an Otto cycle, it's always the same. If it's a diesel cycle, it's always the same. So you should really have Otto, diesel, and Brayton cycle memorized, but anything beyond that, like modifications to it, you don't need it memorized.
Okay.
And then we'll have one in the next chapter, and then one in the chapter after that. So there's a few, and then there's modifications to those, but if you know the basic one very well and understand it, the modifications are really not that difficult to understand once you have the basic cycles down. It's getting those basic cycles down. Okay. Any other questions? All right, well then, I'm actually out of time. If you have any questions or need to contact me or anything, let me know, send me an email. I mean, again, I'll post the solutions to the test maybe right after class here, or if not, it's gonna happen tomorrow. The next homework problems would happen either today or tomorrow also. I've been working on those, the new homework problems numbers to do. All right, so you guys have a good rest of your week, and we'll meet back here on Monday, same time, same place.
All right, have a good one.
Yep.
Enjoy your weekend.